Hello everybody once again. So with this video I'd like to finish up section 2 of chapter 5 of Rife, and in this particular section he goes over the microscopic calculation of specific heats. Although we've already considered the macroscopic case of trying to calculate our specific heats, it's also useful to consider when we're looking at simply microscopic components of our thermodynamic system. It is from these microscopic evaluations that we can relate our macroscopic quantities to something like the number of available states to our system within some sort of permissible energy range. And he begins by actually just starting out with our definition of the number of available states for any monatomic particle in some sort of accessible energy range between E and E plus delta E. And if you remember, or if you're reading along, or I don't know if I've posted videos really going too much into the function omega here, other than maybe like an entropy calculation or two, but that's what that function describes. Allergies, hold up. Okay, I'm good now. Anyway, for a monatomic ideal gas specifically, this is C some constant times the volume to the power of n being the number of particles in our system, times the energy to the power of 3/2 times n. For a diatomic ideal gas, this gets bumped up to 5n divided by 2 in the exponent. But let's just deal with the monatomic case, and if you want to, or heck, if I feel like I'm up to it, I can redo these steps with a diatomic molecule and post that as another video just as a proof to show that you can get the same conclusions using the same essential proof just by changing the constant in the exponent of E. Now, for clarification of the shorthand, I'm letting this function omega EV just be written as omega, and then we continue to evaluate, as has been the standard practice when dealing with the number of available states, because it makes things much more slowly varying. We take the natural logarithm on both sides of our equation, and we can just use our simple properties of the natural logarithm to split up the right-hand side into 3 separate terms, right? We have our natural logarithm of our constant, n times the natural logarithm of our volume, and 3/2 n times the natural logarithm of our E, right? So if we recall that our temperature parameter beta is defined as the natural logarithm of our number of accessible states with respect to energy, and that can also be written as 1 divided by the Boltzmann constant times our absolute temperature, kT. We can evaluate that particular partial derivative and relate it to our temperature parameter beta. So doing so, we notice that not only does our constant term here cancel, but also our volume term cancels, and that leaves us with just the partial derivative with respect to E of the natural logarithm of E, which is just 1/E. So since we have that, we just have this term over here is equal to kT, and then we can actually express our energy of our monatomic ideal gas as being 3/2 times the number of particles that are in that system times the Boltzmann constant times the absolute temperature, which is a very handy relation. Now, if we let our number of particles that exist be equal to our Avogadro's number times the number of moles we have of the number of moles of gas that we have nu, we can rewrite our expression in terms of the ideal gas constant R. So what we essentially express is that our Avogadro's number times the number of moles of stuff we have in our system is equal to R here, which is our ideal gas constant, right? Which works out because Avogadro's number is a constant, and K is also a constant. So with this expression in mind, with E being equal to 3/2 times our nu times R times T, we can actually take a partial derivative of E with respect to temperature and divide that by the number of moles nu, and we can recover the fact that our specific heat for a monatomic ideal gas is equal to 3/2 times our ideal gas constant, and this ends up becoming about 12.47 joules per degrees Kelvin times the number of moles you have. Similarly, if we take a derivative with respect to Q, which we had in our previous video, and I believe we express it as something like dq is equal to dE plus P dV, and then we do some not separation of variables, but we do some substitutions from the ideal gas law. We can take our partial derivative with respect to temperature and then divide by the number of moles that we have, and we actually get that it is equal to 3/2 times R plus R, which gives us 5/2 R, which evaluates to about 20.78 joules per temperature times the number of moles we have. Also importantly, we can recover a discrete value for our value of gamma, which is just the specific heat with constant pressure divided by the specific heat with constant volume, and when we do so, we get about 1 2/3. That's a decimal approximation there. But nonetheless, what we were able to do essentially is that we were able to take the number of accessible states that we have, we were able to relate that to energy of our ideal gas through the temperature parameter, and when we were able to do that, we could take some partial derivatives and total derivatives, and we were able to recover specific discrete values for the specific heats of our substances in terms of our ideal gas constant R.